Welcome to episode 19 of the David Bernard Podcast. Today is October 13th, 2021, and we are going to take a closer look today at the ocean and the role it plays in both strengthening and weakening of tropical storms and hurricanes. Certainly, we've talked some about the strengthening process and the hot Gulf temperatures, but it goes a lot deeper than that, literally and figuratively, but also what can cause them to weaken. And our guest today is an expert in this. Her name is Dr. Nan Walker. She's of Louisiana State University. She is a professor and James P. Morgan Distinguished Professor of Coastal Studies in the Department of Oceanography and Coastal Sciences at LSU. Dr. Walker is also director of LSU's Earthscan Laboratory, which, if you don't know about that, we're going to learn about the Earthscan Laboratory today as well. Her areas of expertise include physical oceanography, satellite oceanography, which we're really going to be focusing on, air and sea interactions and tropical cyclone intensities, the Gulf of Mexico loop current, and eddy circulations. I think you're going to find Dr. Walker's research really interesting, and this type of research we need, especially when it comes to getting better hurricane intensity forecasting models, which we all know is still somewhat lacking, to say the least. Well, speaking of storms, we are finally in mid-October, which traditionally means the chances for a severe hurricane goes down quite rapidly. Now, with everything in the weather, there are exceptions, and last year was one of them. And of course, I'm talking about Hurricane Zeta. For those who may not remember this statistic, and it's pretty incredible, Zeta is the strongest storm on record to hit the United States so late in the season. The previous record was the Tampa Bay hurricane on October 25th in 1921. Now, initially, when Zeta made landfall, it was a 110 mile per hour Category 2 storm, but it ended up being reanalyzed as a Category 3 with 115 mile per hour winds. And while that didn't make a difference really in the impacts, certainly it does from an historical standpoint, making it a Category 3 and the strongest storm so late in the season to hit the United States. The National Hurricane Center does this post-analysis every season with all the storms. The same is going to be done this year. And of course, of particular interest to us in Southeast Louisiana this year will be Ida, that now stands with a landfall at 150 mile per hour winds. I know some of the folks in the coastal areas that went through the heart of Ida think it might have even been stronger than that. But regardless, that was a major intense hurricane. So intense, it ties for the strongest Louisiana landfall on record as far as wind speeds are concerned. Now, as far as October goes, weaker storms have wreaked havoc. We had one in 1985. The big deal with one is it stalled and caused tremendous flooding for days and high water from storm surge. That was at the end of October, the very end of October and leading up to Halloween. But the chance of a Zeta-like storm, again, if we just look at climatology, is extremely unlikely, especially for so late in the season. So on that note, let's bring in today's guest to talk about oceanography, Dr. Nan Walker. Nan, welcome to the podcast.
Thank you. Thank you so much, David.
Well, I want to say I started talking with Dr. Walker, and she's told me I can call her Nan for the podcast, but we started talking before Hurricane Ida. That's when we first planned to do this podcast, and obviously Ida had other ideas. How did you do with the storm?
Oh, with Ida? Well, we were very lucky in Baton Rouge because it appeared at the end the eye just moved to the east of us. So we dodged a bullet again in Baton Rouge. So we were happy about that. Not so happy for folks east of us. I'm sorry that y'all had such damage in New Orleans. It was the scariest hurricane I have ever experienced in Louisiana, for sure.
Yeah, I've told people that. I mean, the area between New Orleans and Baton Rouge just devastated. But even for in New Orleans, just from my personal experience, it was the worst hurricane I've ever been through. Probably before that, the worst one for me that I personally experienced was Hurricane Wilma in South Florida in 2005. Well, we're going to talk today about the water. That's what I was
All
telling
right.
everybody, and how important it is. But first, on a personal note, how did you get interested in oceanography, especially as it relates to tropical storms and hurricanes?
Okay. Well, I'll just mention that my first passion was marine biology. So I did a bachelor's in marine biology at Duke University. And the last two semesters, well, yeah, the last two semesters at Duke, I was at the Marine Lab. So I was started to do field work there and experience more of, the real world. And then I spent a 6 weeks period on a 125-foot sailing research vessel off the coast, off the east coast of the U.S., and just happened to be on the vessel and experienced explosive cyclogenesis over over us and saw 30-foot waves build in 30 minutes and just happened to be the one at the helm at the time. So it was a pretty amazing experience, one
Well,
never to forget.
I would say so. 30-foot waves. I don't get seasick. I haven't done 30-foot waves though before, so maybe I haven't been completely tested.
It's like the perfect storm situation, if you can envision that. Anyway, but my official training, well, I just kind of happened into the field of satellite remote sensing and air-sea interactions as a master's student at LSU and trained with some of the pioneers in this kind of field of research. So I feel very fortunate to have been able to train with some of the best early on.
Well, you wear a couple of hats at Louisiana State University, but I'm particularly interested in, and I've known about it for some time, is the Earthscan Laboratory at LSU. What exactly does the Earthscan Lab do, and its type of research and its history?
Okay, I'll give you just a brief summary because it was founded 33 years ago, so it's done a lot of people have done a lot of things in the lab over the years. But basically, the lab has the capability of tracking the Earth orbiting satellites that NASA and NOAA are responsible for launching locally. And we take that, we track the satellites, they transmit data in real time. We receive that data in real time, and we make that into quantitative measurements of the ocean and atmosphere, and especially the imagery that people are so fond of. And so we track hurricanes and ocean currents and even coastal currents. So we use it in our research. We use it to train students. Over the years, we've hired probably 100 students that have trained and learned how to process imagery in the lab. And I guess we're best known probably for our work with the Office of Emergency Preparedness in the early days when no one had access to imagery of hurricanes or abilities to track them. And our small lab with the system that we had was could track hurricanes in real time and provide this information to the state, which was really very beneficial to them. And then we tracked ocean currents for a project called Eddy Watch. It's basically tracks the loop current and eddies in the Gulf, and so we were a data provider for an organization called Horizon Marine that provides that data to the oil and gas industry to make their operations safer. So those are just two of the things we've done over time.
Very nice. Your one of your specialties, or maybe it is your specialty, satellite oceanography. That's kind of a cool title. What does that mean exactly when you put those two
Well,
together?
it, it, basically it means just using satellites for studying ocean processes and ocean problems. So there's a variety, many different subfields within satellite oceanography. My main field of expertise from way back to my master's is quantifying sea surface temperatures and using those to understand ocean processes, air-sea interactions, for example. But it takes more than that particular area subfield now to track ocean eddies. We use also sea surface height now. So it's with with the different subfields comes different, um, a whole lot of different ways of processing the data and interpreting the data. So it never is boring. There's always things to learn in this field of study.
So let me ask you this. So, and to explain to our listeners, we have these satellites, and especially in the last 40 years, really since the early 80s, I believe, we've been able to use this kind of satellite sensing technology to get a really good overview of ocean temperatures globally. I mean, not just the Gulf of Mexico, but people are saying, well, wait a minute, aren't satellites used for clouds? And how can you get an accurate measurement of ocean temperatures if you have, say, a bunch of clouds over the Gulf of Mexico?
Gotcha. So yes, the Gulf of Mexico is very cloudy, and in general, tropical areas are very cloudy. Um, so So to use the sea surface temperature as a climatology variable, you have to get rid of the clouds. So NOAA actually creates most of the imagery that's used in climatology, and what you were referring to in the sea surface temperature measurements started in the late 70s, and that's kind of when I started my master's. So the same, actually, it's the NOAA AVHRR sensor, which was the first one that we could track in the Earthscan Lab. Um, that that data set extends for a 40-year long period, so it's a very very valuable record of sea surface temperatures. But NOAA takes very big precautions not to include clouds in that record of sea surface temperatures. So it's a very well developed technique using multiple um, multiple tests to get rid of the clouds so that we're sure we're only looking at ocean temperature.
And I think we had talked about you have a declouding method that you
That's
guys have
right.
used.
That's right. So the declouding method, um, basically, it's so if you look at the ocean temperatures and compared to cloud temperatures, the ocean temperatures are warm and cloud temperatures are cold. So what we do, the one of the important things that our lab was, one of the capabilities that we obtained in the mid 90s was to have access to the weather satellite. Goes east, covers the our area, the northwestern Atlantic. And so the goes east measurements were available every 15 minutes. So if we look at a nighttime series of data, we take a 10-hour record with 4 images per hour, and we retain the warmest picture element at each pixel location within the image and create a new image with just the warmest
Hmm.
pixels. And that would be likely the cloud temperatures. If the cloud, I mean, the ocean temperatures, if the clouds don't move, then we have a problem. We can't get rid of clouds that don't move. But if they move, if the clouds are not completely uniform and they move so that an ocean pixel becomes clear, then we have an ocean temperature. So it's
And
basically we create a whole new image that is a recreation of the nighttime sequence of images. So, and the only reason we can do this is that the ocean moves very much more slowly than clouds.
yeah,
So,
so
yeah.
so I guess I mean maybe would that be easier, say like in the summer? I guess I mean versus the winter when you might get like huge stratus decks over the Gulf. The summertime, the cloud cover tends to be more variable and breaks up. And of course, that's where you're most interested, I think, is because of your study of tropical storms and hurricanes.
Right, right. So, yes, exactly. Probably clouds don't always, there's more cloud cover um, of the stratus type in the wintertime for sure. Summer, of course, you can't see through a hurricane, so we have to, if we want to look at the pre-hurricane and post-hurricane sea surface temperatures to see what the cooling was and where it was, then we have to go several days before the hurricane entered the Gulf, and several, you know, at least we have to wait for the clouds to clear out afterwards.
And let's get to the heart of this and really start talking about ocean temperatures, where your research has really been focused. And I guess we'll start by talking about warm water. But just in general, water temperature is important, but it's not just the surface of the water, it's how deep it is as well.
Exactly. So sea surface temperature has been known to be important for hurricane intensification and maintenance for many years, and there's a critical threshold in sea surface temperature, which is about 26 degrees Celsius or 79 degrees Fahrenheit. But the sea surface temperature is only the top meter of water. That's by definition. Um, what's more important is the depth of the warm water, because that's where the hurricane's fuel is, and through latent heat flux or evaporation, which is and the evaporation from the ocean cools the ocean, but it fuels the storm through condensation and precipitation. So yes, the depth of the warm water is critical. And in the Gulf, there's areas that have very deep warm water, and then there's areas where the cold water, which is naturally happens as you go down in the ocean, the water gets cooler away from the sunlit or the sun warmed area, then that cool water is very close to the surface relative to the warm features. So we have warm eddies and cold eddies, and we have the loop current, which is the ultimate source of warm water to the Gulf.
So that's water depth, and you started to kind of get into it. So we have water depth, and then we've got water temperatures, and then we have these circulations. And some of our listeners may be familiar with that, the loop current in the Gulf of Mexico. For those who aren't, maybe you can explain a little better what it is. I think for the folks that have heard of it, the first time that I think it was out there in the general public really was in 2005 when we had the Katrina, Rita, Wilma events. But exactly, what is the loop current?
Okay, so the loop current is a very warm, deep, high velocity current. It's part of the very large subtropical gyre in the North Atlantic, and it's a source of water to the Gulf Stream off the east coast of the U.S. So the source regions for the loop current, the source region is the Yucatan current, okay, which flows through the Yucatan Channel. And so as the Yucatan current flows into the Gulf of Mexico, it's renamed the loop current. The loop current undergoes a large loop in the Gulf of Mexico because it exits the Gulf via the Florida Straits, is the Florida current. Again, just a renaming of a flow. So the loop part of the loop current typically, is most prevalent at about 27 degrees north. So that's about the latitude of Tampa, Florida, on the west coast. But the loop current is extremely variable. It's highly dynamic, and it's yet unpredictable by numerical modelers. So sometimes it surges very far north. So before Ida hit the coast, it had surged north to 29 degrees latitude. So that was very close to the edge of the continental shelf. So very close to land, actually. So that means that close to land is a very warm pool of water. In fact, the whole central eastern part of the Gulf was full of very warm loop current water. And
Yeah,
it was
and
in the process of shedding a big warm core eddy. So there was a lot going on in the Gulf region at the time in terms of the loop current.
yeah, we're going to talk about, so we have our currents and we're going to get into eddies as well. But I just want everybody out there to know, as we mentioned at the beginning of the podcast, I began speaking with Nan before Ida. I think it was like a week and a half before is when I first contacted you. And I believe it was on the 25th or the 26th, I think, when Ida first became a depression. You said, hey, a colleague of mine attain this image. You sent me an image that was an analysis of the current loop current. You said, look how far north this is. And I got to say, I looked at that and I just thought, this is going to be bad. This is not going to be good. That was pretty dramatic, that imagery.
Yes, that was a sea surface height image. So in the summertime, the Gulf becomes very isothermal, which means it's uniform in temperature at the surface. But again, that might just be the top meter. Generally, it's more. But so we use sea surface height. Sea surface height tells us where the warm and cold features are in the Gulf and allows us to map the loop current. These are very large features, so and sea surface height looks through clouds, so we don't have a cloud problem. My collaborator, well, a longtime research collaborator of mine makes a very good product of sea surface height, and he was the one that provided that. His name is Robert Laban in University of Colorado. So it's a very accurate product, and the problem for Ida, or the problem for us, is that Ida, after it left the coast of Cuba, it tracked for over a day in the loop current. So the whole time it was, the central portion of the hurricane was taking up the fuel out of the ocean, and over the loop current, in the loop current, there's so much heat. It extends down as much as 400 or 500 feet. So there's no way that a hurricane will ever take all that energy out of it. So it's just an unlimited supply of energy.
And we're going to I was going to say, we're going to talk about the impacts that cold water and eddies and circulations can have on hurricanes. But I think what you just pointed out there, if we talk about 2005, where you said it's just an endless amount of energy because of the depth of this water, the loop current. 2005 is an excellent example of you can have these monster storms move over the loop current and there's really no degradation of the water temperature.
Exactly. Occasionally we see the water temperature at the surface drop by about a degree or two Fahrenheit, but that's nothing that's not anything compared to what happens when the cooling that happens outside of the loop current.
Because we had Katrina, Rita, and Wilma pass over it that year.
Yes. Katrina was not on exactly the same path as Ida, but it tracked over the loop current for over a day, probably 2 days. And it, just like Ida, it underwent explosive development over the loop current. In the case of Katrina, well, we can talk about cold core eddies later.
Yeah, well, we're getting to that in just a second. I wanted to get your thoughts on, because just so everybody knows, Dr. Walker she is all about the cold core eddies. I think this is really the most, I think, interesting aspect and the heart of your research that you've been doing over the years. But I did want to get your comment on these rapidly intensifying hurricanes. We can look past Katrina. Just in the last 5 years, Harvey, Michael, Laura, Ida, we're getting these explosive developments. Is this? I do know that the Gulf has been anomalously warm the last 5 years compared to the historical record, which, as you mentioned, goes back to at least what we have satellite sensing, the late 70s, early 80s. What are your thoughts on that? Is this bad luck? Is this like something permanent that's going to be occurring?
Well, I don't think intensification over the loop current is a new thing, because wasn't it Betsy that hit the Louisiana coast? No, Camille. It was Camille, which intensified over the loop current as well. So it's not a new thing. It is true that research has shown that the Gulf sea surface temperature is warming slowly, not nearly as fast as some places in the world, like in the polar regions. That's where we have most, the greatest amount of warming in the sea surface temperature. But it is a factor. how I still think, the major factor is what features the hurricane is tracking over, because a small amount of sea surface temperature rise is not going to do quite as much as a hurricane tracking over a warm core eddy or the loop current. It's you know just the scale of the heat content is immense, because the loop current is bringing, well, I'll tell you what it is. We measure ocean currents in volume, and we use something called a Sverdrup, but that's not that important. The loop current introduces a superdome of water every second into the Gulf of Mexico. That gives you an idea, like the volume of the
Okay,
superdome.
we understand a
every second.
superdome. Okay, we got that. See,
Yeah.
now you're talking on my level there. I got that.
Yeah, right, right. So it's just an enormous amount of heat that's coming into the Gulf of Mexico every second.
Okay, well, that's everything that can go right for a hurricane, all right? But
Right, right,
let's talk about what can go wrong for a hurricane, and I think that's what we really want to have happen, right? Is what can
right.
go wrong for a hurricane, and most people out there listening know that cold water is bad for a hurricane. So,
Yeah.
when you look at these the process that can cause that, upwelling and cold core eddies. Is the same are these the same processes that can weaken hurricanes that strengthen them? It's just you have an opposite effect. Does that make sense?
It's not quite that simple, but you know, but basically, yes. So the warm features intensify hurricanes because they provide an unlimited amount of fuel to the hurricane. The cold core eddies, interestingly enough, my research showed that the the low pressure system, which is the hurricane, intensifies a cold core eddy because it's actually the equivalent of a low pressure in the atmosphere in the ocean. So they both circulate the same way, counterclockwise. And so when one couples with the other, the atmospheric system intensifies the ocean system. The cold core eddy is already an area of upwelling, meaning that in the center of the cold core eddy, the cold water is bulging upwards towards the surface.
Okay,
So,
to back up just a minute, what
okay,
exactly is an eddy,
okay,
and what causes them?
okay. So an eddy is basically a circular current. Okay, so a cold core eddy is rotating counterclockwise, and it's analogous to a low pressure system in the atmosphere, like a hurricane. They rotate in the same direction. Um, the warm core eddy is rotating clockwise, and it's analogous to a high pressure in the atmosphere. So the ocean and the atmosphere are two fluids that move in, that have a lot of similarities, although the scale, the the um, the motion scales are much quicker in the atmosphere, obviously. Okay, so what causes them? Okay, so eddies, basically the cause of the main force for driving surface ocean circulation is the wind. Okay, that's the main force in the ocean. We have other forces like Coriolis and pressure gradient, but wind is the driving force. So initially, eddies are caused by wind. They're also caused by interaction with other eddies or major currents like the loop current, or even interaction with like bottom topography. Um, so I know, we don't want to get too much into the details there, but that's the basic cause for eddies.
So yeah, so let's talk about some of those examples, because your research has been the impact of these cold water eddies and circulations on tropical systems. One storm we were talking about in particular was Ivan, in 2004. Just to remind people out there, or those that may not be from the Gulf Coast area that are listening, Hurricane Ivan was a very powerful hurricane. I think it was a Category 4 when it went across the western tip of Cuba. Then it moved into the Gulf, and it caused a major evacuation of the New Orleans area, which was sort of a, well, it wasn't. It was a big mess, the evacuation itself. But at least for southeast Louisiana, Ivan ended up going east toward the Florida Panhandle. But your research showed something pretty interesting about Ivan.
Yes, in fact, it took a while to understand what we were looking at. So Ivan took all the clouds with it. It was amazing. So within a few hours of Ivan, well, immediately after Ivan passing over the Gulf of Mexico, it cleared out and we could see the features in the ocean, which is not always very, very normal. Usually there's still some remnant clouds. So what we saw were these two huge areas of very cold water. And it took us, we had to combine the sea surface temperature with the sea surface height data to understand how these coolings related to the eddies in the Gulf. And what we found was that it was very clear that the coolings, which were extreme, down to, let's see, the water temperatures were well below the minimum threshold at the surface for a hurricane. The minimum threshold is 26 degrees Celsius. The minimum temperatures we found were 20 degrees Celsius.
Wow.
And they were centered in these cold core eddies. In fact, they defined the cold core eddy. And so we, took several months to analyze the data and finally had, an idea of what had caused them. And it was like kind of no one had ever observed such a dramatic link between the cool wake of the hurricane, which is the maximum cooling area under a hurricane, and cold core eddies. And it just so happens the Gulf has very, very intense cold core eddies. They extend 1,000 meters down in the vertical, just like the warm core eddies. They also extend very deep. But the important thing is that the cold core eddies have this dome of cold water that's sitting at about 150 feet down in the water column, and the hurricane intensified the cold core eddies. And in addition to that, the waves were extreme in Ivan. They were 80-foot waves, maximum waves, and they helped to entrain that cold water up to the surface as well. So there's several different processes at work, but all moving to all of them work together to get that cold water rapidly to the surface.
So, and what you're saying there, because of Ivan's intensity and it was happening to passing over these cold water eddies, it was almost like a feedback, right? It was almost like Ivan was sort of working against itself. It was helping to intensify these cold water eddies.
Yes, exactly. Ivan was intensified the cold water eddies. The cold water eddies were separated by a warm water eddy. So that was interesting. A warm eddy had just separated from the loop current, which is, the warm eddies are always north of the loop current. In fact, the warm eddies are the northern part of the loop current that separates off. That's a whole nother interesting story. So there was a warm core eddy, and there's always cold core eddies around the loop current. And when the northern part separates off, they take the cold eddies with them. So the cold eddies and the warm eddies actually both originated at the loop current. Anyway, so we have cold eddies between the loop current and the warm eddy, and then we have the warm eddy, and then we have another cold eddy north of the loop current. So despite the warm eddy being there and Ivan tracking over the warm eddy, the cold eddies provided enough negative feedback to the intensity that it actually weakened as it moved over those features. So the wind speed decreased as it moved north over those features.
Let's talk about Katrina. What did something similar happen with Katrina in that case? As we know, Katrina was at its peak over the loop current. It was a 170, 175 mile per hour Category 5 storm. By the time it reached the Louisiana coast, it was a Category 3 that was unwinding. And I always try to explain to my viewers, I say, look, if you have a Category 3 storm with 125 mile per hour winds that is weakening or winding down, that is going to be a weaker storm than if it's a 125 mile per hour hurricane and it's ramping up. The physical process is just that's going to be a more intense impact. But Katrina was actually unwinding, at least from a wind standpoint and structurally.
Yes, that was very fortunate that that happened. Otherwise, it would have been, a little much worse. Yes, we observed that as well. So the loop current clearly was the force of fuel for Katrina, and it exploded rapidly, just like Ida did, over the loop current, and it traveled over it for some time. And then there was a cold eddy north of the loop current. So as it left the loop current, there was actually another warm core eddy in the process of forming, but it was loop current water. So the cold core eddy north of the loop current, um, again, provided the opportunity for the hurricane to bring up cold water to the surface, and it provided some negative feedback to the hurricane, again, weakening the hurricane. Not by a huge amount, but from Category 5 to Category 3 is pretty much a lot of weakening. There may have been other factors that also contributed. So, but that, but it clearly, we had to wait a couple days before we could clearly see the cooling in the cyclonic eddy offshore. But it clearly was there, and it was very similar to the Ivan situation. So we would expect that it played a role in the weakening of Katrina.
Another example that really sticks out in my mind, and we discussed this over email, and you even went back and looked at it. You hadn't looked at this storm before, and that was Lily in 2002. And I'll never forget sitting in the weather office and watching the latest vortex message come in from the hurricane hunters, and there was this explosive drop and pressure, once again traversing the central Gulf of Mexico. And all of a sudden, we were looking at a Category 4 storm heading for the Louisiana coast, which was the most powerful storm to approach the coast since Betsy, if that had maintained itself. And I'll never forget it. It's like literally that storm evaporated at the coast. I mean, it was, I'd never seen a storm fall apart so fast like that. It really became just almost a puff of wind. Were there several meteorological things going on, or was it mainly oceanographic? Or
I remember Lily well as well. It was one never to forget. I remember the intensification. I was actually at a conference in Colorado and walked into the main, gathering room, and it was a conference on the new GOES satellites. So there were lots of hurricane animations. I walked in and looked at the screen and went, "Oh, what hurricane is that?" Thinking it was a hurricane and, a historic hurricane. I was like, "That's Lily," and it just exploded over the loop current, and we got to get home.
oh gosh,
So that was awful, and we had a hard time getting home too. And then, preparing for a Category 4, hurricane to hit, we were, how do we prepare for a Category 4 hurricane? Well, we did everything we could, and then go to bed and wake up and the storm had died. And it was more than that, because we were actively assisting with the Office of Emergency Preparedness with tracking and understanding changes in the hurricanes. And obviously I wasn't there, but some of my colleagues were watching. But one thing that happened is that the GOES, or the weather satellite, which we use to track hurricanes, had to be turned off. It has to be turned off during a part of the summer, and it's due to the fact that the sun will burn out the electronics. So at about 2 in the morning, NOAA turned off the GOES satellite, so we couldn't track the hurricane. Nobody could track the hurricane. So it was a surprise to everybody when you know, when it collapsed off the coast. It didn't collapse to nothing. I think it was a category 1 or 2, 1 maybe when it hit the coast. But
Yeah, but again, it was unraveling, and the impacts ended up being
right.
pretty minimal. Was there anything going on at the surface there, the water that led to this?
Well, um, I spent a lot of time looking at the data we had, and at the time we only had the sea surface temperature data. We weren't actively like integrating the sea surface height, which we did later. Um, so it looked like Isidore cooled the Gulf substantially because Hurricane Isidore had tracked across a similar part of the Gulf just 10 days before,
Hmm.
and it cooled the Gulf several degrees. Um, and then one of my colleagues was looking at the atmospheric component, and he found that there was dry air which had advected into the western side of Lily, which is not too unusual when storms, get into the northern Gulf. The dry air, I guess, is coming off the coast of Texas. And then, of course, the governor was telling everyone that it was the power of prayer that had saved the coastal residents. So there were a lot of different viewpoints. But after you asked me about Lily, I went back in our archive, in the Earthscan Lab image archive. So we have, and for some products, we go back to 2000. So we covered Lily, and we had a product that I had produced after Ivan. We started this product. So we took our sea surface temperature image and we overlaid the contours of sea surface height, which showed us where the warm and cold eddies were. So what I saw just amazed me because it kind of solved the problem. Because what happened was Lily moved, it intensified over the loop current, but the loop current was not extended far into the Gulf. And so it tracked a long time. It tracked over a large area of the Gulf after it left the loop current. And what I saw in the Gulf was a lot of cold core eddy circulations. So there was in terms of ocean heat content, it did not have the fuel that some of the other hurricanes have had. And also there was a lot of cold water on the continental shelf. And this cold water, funny enough, probably was there because of Isidore for two reasons. One, Isidore brought cold water up from just wind entrainment along, in shallow water. And also, Isidore caused offshore winds near the Atchafalaya Bay, which has a lot of river water discharging there, and the offshore winds increase the flow of river water onto the shelf. And the river water coming from farther north is relatively cold. So there was a lot of cold water that Lily was exposed to, which we did not know, before the fact. And in fact, we did not know that, the imagery was not very good after Isidore or after Lily. There were not clear coolings in cyclonic eddies like we saw after Ivan. And I think there was just a lot of water vapor in the atmosphere, which messes up our readings of the ocean. So it was
Yeah,
it's a whole complicated story with Lily,
I think
but it
so.
turned out well for coastal residents.
All right, so what we've talked about today is we've talked about eddies and circulation and water temperatures of the Gulf and the importance of the depth of water temperatures, whether it's hot or whether it's cold. Um, all of these features, some of them are small, some of them are large, they really do make a huge impact on these storms in the Gulf. And what I learned today, what I thought was so interesting, is that these cold water eddies can be almost as extreme as the warm water ones. So I don't know if that's nature's way of trying to balance things out, but the Gulf of Mexico is it's a complicated body of water.
It is for sure. The Gulf of Mexico is full of eddies, that's for sure. And if, you know, it's we have the technology to provide a surveillance of the eddies daily, and how they're changing daily. So it would be it's very important information to somehow get into the numerical models that can predict hurricane intensity. And I think there is a big push to do this. It's, something that hasn't been done before. So, getting the information that's needed in a timely manner to input into the models is, it's a little complex, but not insurmountable.
Yeah, and that's interesting, and for our listeners, we're talking about when you forecast hurricanes, they know we have the track aspect of the storm and the intensity aspect of the storm, and the intensity forecasting, as we've talked about on many occasions, has lagged behind the trackability, but perhaps getting these features and this data inputted into the models, these small features. Maybe that will give us a little more insight on this intensity, and we won't be as so surprised by these Lauras and these Idas, or even the Lilies, the ones that maybe unravel very quickly.
Right. Well, I was impressed with Ida. Our local weatherman in Baton Rouge had a similar image to what I showed you of the loop current, and he was explaining how Ida was going to intensify over the loop current. So at least, the meteorologists are now talking about the ocean features. So somehow they're getting this information. So that's a first step. It's taken quite a long time for this first step, but it's happening. So I think, in the next few years, we'll see hopefully a big improvement in intensity forecasts.
Well, Dr. Walker, I will be glad to communicate anything that you send to me to our viewers as well. We're on top of the science here at Fox 8 as well. And again, all of the researchers at LSU are really doing some valuable work. And I appreciate your time today and being on the podcast.
Well, thank you. It's been fun to be on the podcast. I hope that your viewers understood a little bit of what I was trying to say.
I'm sure they did. You were quite clear, and we have a lot more to learn. That's definitely the case. Have a great day.
All right. You too. Thanks, Dave. Bye-bye.
I think it's pretty clear that we have some very important research going on right here in Louisiana when it comes to hurricanes and tropical storms, and Dr. Nan Walker is right there at the center of it. Again, this is being recorded on October 13th, and all looks quiet in the tropics. We've had big breathers ever since Nicholas and Ida, not just here in the Gulf, but along the east coast of the United States as well. And of course, that is welcome. And with each week that goes by, our chances for those major hurricanes continue to decrease. If there's any change, of course, we'll let you know on Fox 8, and the entire team there is keeping you ahead of the storm as always. Shelby, Zach, Nikonder, Bruce, we're going to be there for you right on up to November 30th when it officially comes to a close. A reminder that if you're listening to this podcast app, that's great. If you're not, if you're watching the video version on our website, you can download the David Bernard Podcast app on any of your favorite podcast apps just by searching for the David Bernard Podcast. And if you want to watch the video version, it's on our website, fox8live.com/David. I'm Chief Meteorologist David Bernard. Thanks for listening, and we'll see you on the next episode.